Thanks very much for the opportunity to speak here. So everything I'll tell you today is about work in progress with Daniel Jafferis, and hopefully that work will appear soon. So as some general motivation for my talk, the last few years have seen an explosion of interest in construction of supersymmetric theories by reduction from 6 dimensions, and that provides an interesting geometric perspective on various aspects of these theories, for example, dualities or BPS states, and many other phenomenon. In a parallel line of development, there's also been a lot of progress on supersymmetric localization, and that's led to a whole host of new computable partition functions for supersymmetric field theories. My talk today will be at the intersection of those two disciplines. So frequently, when you have a quantum field theory with a 6D parent, you get a novel interpretation for various supersymmetric partition functions. So let's get a little more specific right away. Today, I'll start with the 6D theory of parallel M5 branes, the 2-0 theory, and I'll put it on the product space of the 4 sphere times the Riemann surface, and I'll try and compute some partition function z. So to begin, we should ask, what can z depend on? And it's important that since the 6D theory is conformal, z can't depend on, and since we put the theory topologically on sigma, z can't depend on either the volume of sigma or the volume of S4. That fact allows us to develop two distinct interpretations for the same quantity. So on the one hand, we can first think of sigma as being very tiny. In that case, we'll reduce to some 4-dimensional effective field theory, which is an n equals 2 field theory. These are the famous class S theories that have been very well studied. And then we can put that same theory on whatever it is on S4 and get this quantity z that we were originally interested in. Alternatively, however, we can think of the S4 as small first. Then our reduction will land us on some 2D quantum field theory, and we can put that quantum field theory on sigma to compute the same partition function. So this is what's called the 2D 4D correspondence. So famously in this context, Aldai, Gayoto, and Tachikawa conjectured that the theory that you get by reduction on the 4 sphere is the Toda conformal field theory. So as a little reminder, if you have n parallel M5 branes, the Toda theory will have n minus 1 real scalars, and has a Lagrangian that I'll flash here. It's got a standard kinetic term and an exponential potential. Okay, so what's the punchline? Our result will be a derivation of Toda theory via dimensional reduction from 6 dimensions. How can we do this? We're often told that the 6D theory is quite mysterious. Well, our method is one that's been pursued by many groups in a variety of contexts, is to factorize the dimensional reduction. So instead of putting the 6D theory on the 4 sphere first, we'll just reduce on a circle and get to 5D super Yang-Mills, and then we'll put 5D super Yang-Mills on this quotient space S4 times S1. Okay, why does that work? Well, okay, so if you reduce the 6D theory on the circle, it's only 5D super Yang-Mills at very low energies. In our case, however, we're interested in the limit where the 4 sphere is very tiny. Therefore, the circle that we reduce on is very tiny. And that scale suppresses all the higher derivative corrections. Another more technical reason why we can ignore higher derivative corrections is that they're Q-exact. So they're the analog of D terms, and their coefficients can't enter our calculation. Now, there's something funny about this reduction. This quotient space here, S4 mod S1, is singular. And so another thing to worry about is, does it really make sense to put 5D super Yang-Mills on that space? So you can get rid of that fear if you note that the 5D Yang-Mills coupling, G Yang-Mills, is set by the radius of the circle that we reduce on, and that that radius goes to 0 at the locus of singularities in the quotient space. So therefore, we'll be able to understand these singularities in terms of some weakly coupled 5D physics. Okay. So now let's get more specific. In order to get more specific, we're going to have to develop a point of view on the 4 sphere. So I'll start in 6 dimensions with compactification on S4 times 2D Minkowski space. Notice here that I've replaced the Riemann surface by the 2D Minkowski space. that's because I'm interested in determining the effective field theory, so I might as well ignore the topology of the Riemann surface. This compactification has OSP 2/4 symmetry, and we want to reduce to 5 dimensions in a way that preserves some of that supersymmetry. So pictorially, that means we have to think of the 4-sphere as follows. So we'll find an equatorial 3-sphere. So this 3-sphere here that I'm drawing is the equator of the 4-sphere. And we'll view it as a hop fibration. So S1 fibered over S2. And then we obtain the 4-sphere by having the 3-sphere vary along an interval and shrink at the north and south poles. So we're going to want to reduce from 6 dimensions to 5 dimensions along this S1 that I've highlighted here. Okay, that is possible to do, but it's technically quite complicated. After all, the radius of this circle sets the 5D Yang-Mills coupling. That's clearly varying along this interval. So you're going to have to deal with quite a complicated system. Luckily for us, there is an important trick. The important trick is to note that the 6D theory is conformal, so its coupling to background supergravity enjoys Weyl invariance. And we can do a Weyl transformation of our geometry to simplify the problem. So what we'll do is we'll stretch the interval that I've drawn here to infinite length. So that replaces this 4-sphere by this space. So the 4-sphere just becomes S3 times an interval. The important feature is now that S3 is at constant radius. The price that I pay for that rescaling, however, is that the metric is no longer a product metric. Instead, you get this interesting metric here. So the metric on the 2D Minkowski space has become warped by this interval coordinate z. And the data of whatever was happening at the poles is now mapped to some kind of boundary condition at z is plus and minus infinity. Okay, so with those geometric preliminaries, I can now tell you our more detailed plan of attack on this problem. So we reduce from 6D to 5D on the hop circle of the S3. The S3 is now constant size because I've done the Weyl rescaling. Then I'll land in 5D super Yang-Mills on S2 with 1 unit of graviphoton flux, and I'll reduce to 0 modes there. I get some 3D theory, and I'll put it on this manifold, which is just really R12 as a manifold, with this funny metric. This funny metric, by the way, has some interesting features. It's for example, as z goes to plus and minus infinity, it's asymptotically ADS3. That plays a significant role at some moments in the calculation. The next step is to add suitable boundary conditions at these ends, z is plus and minus infinity, and then we'd like to determine the effective action for the boundary degrees of freedom. Okay, so we seem to have our work cut out for us, but luckily the first non-trivial step was actually solved last year. So the first non-trivial step was to put 5D super Yang-Mills on S2 with 1 unit of graviphoton flux, and myself and Daniel Jafferis, as well as another group, studied that problem last year. And what we found is that the low energy degrees of freedom are a complex SLNC gauge field B. So B you can think of as A plus IX. A here is your ordinary SUN gauge field. And X is a triplet of scalars from 5 dimensions that have now become twisted to 1 forms and are naturally combined with A. The Lagrangian for your system is just this sum of Chern-Simons terms for B and B bar. And you're meant to integrate independently over A and X in the path integral and quotient by SLNC gauge redundancy. Okay, that's a simple answer, but it's somewhat puzzling. You see, we started in 5 dimensions with an SUN gauge theory. I did some supersymmetric compactification of that theory. So if life is just, you would think that my effective field theory that I should get, not SLNC Chern-Simons in the way that I've just described it, but rather SLNC Chern-Simons in a gauge. In a gauge where SLNC is broken to SUN by an SUN covariant Lorentz gauge that sets the divergence of X to 0, and you indeed find the fermions that you expect by supersymmetry, but they're reinterpreted as Faddeev-Popov ghosts for that gauge fixing. So I mention this here because in our setup, many things are more natural to work out in this gauge because that's directly what the 5D theory gives us. So I'll proceed in the following working in that gauge. And notice also that that provides a way for that funny metric, that warped metric, to enter because this gauge uses the metric. Okay? The next step is to work out the boundary conditions. So how can we work out the boundary conditions? So I'll zoom in first of all on one boundary. Say z is infinity. That's the region that was a pole of the sphere. Let me change coordinates so the boundary is at 0, and w will be a transverse coordinate to the boundary. We can get an intuitive picture on those boundary conditions by thinking about them from the relationship between M theory and type 2A. So we started in M theory, if you like, with the 6D theory of parallel M5 branes, and we reduced along a circle, so we get a stack of D4 branes. That's the place where the 5D super Yang-Mills lives. Now, the circle that we reduced on has vanishing radius at, say, the north pole of the 4-sphere. That's a locus in M theory of dimension 7. So when we get down to type 2A, it's a D6 brane. So the boundary condition that we're looking for is the boundary condition where a stack of D4 branes ends on a single D6 brane. Okay, that, of course, is very well studied. So that boundary condition is what's called a nom-pole. So the scalars x diverge as you approach the boundary. That's illustrated pictorially here with this kind of spike. So physically, you're supposed to think of the D4 branes kind of pulling on the D6 brane. And the displacement from the center of axis of this central axis of this spike is the scalar field, and clearly it blows up as you move into W is 0. The coefficient of the pole here is also constrained. It's supposed to be valued in an SU2 algebra. So those TAs commute to the SU2 algebra there. So that takes care of the scalar boundary condition. The rest of the boundary conditions are fixed up by supersymmetry. So, for example, our connection A will have to be such that the SLNC gauge field that I introduced, B, is flat. That means that B should have the following structure. Its W component lies in a Cartan generator and has this pole. And it has a kind of chiral pole here. So here x plus is one of the light cone coordinates in the xt space. And it has no x minus component at leading order. So that's the fixed boundary condition. Where do the fluctuating fields come from? So the fluctuating fields will come from here in terms that are less singular in W. And we'll see that they give rise to a chiral Toda theory. So if you like, the executive summary of the question, what are the Toda fields in the AGT correspondence, at least from the point of view of 5D Yang-Mills, we're going to have an answer that the Toda fields are modes of the 5D scalars that are localized at the poles of the 4-sphere. And this is similar to a point of view advocated in work by Nekrasov and Witten. Okay, so let's be somewhat more explicit. So the boundary theory of Chern-Simons is well known. If you have Chern-Simons on a manifold with boundary, you get a WZW model, and we can use that as an intermediate step. So we take the field B, which is our SLNC connection, and it's flat. And it's flat so I can think of it as, roughly speaking, pure gauge. So I write it in this form. So F here is a background that's giving this nom-pole. And this matrix H that I've written here is going to give the dynamical degrees of freedom. So what are the constraints on H? So H obeys the following conditions. First of all, it's SUN valued and not SLNC valued. That's an important reality condition. So how does that come about? Remember, we were working in the gauge where the covariant divergence of x is 0. And it's an interesting fact that on the manifold that I am working on, that warped product, the non-pole background actually satisfies that gauge condition. And therefore, SLNC is fixed to SUN, so H can only fluctuate in an SUN direction. We'd like to think of H as giving some boundary degrees of freedom, so it should be thought of as a function only of x plus and x minus, the light cone coordinates on the boundary. It gives fluctuating actual degrees of freedom because it doesn't go to 1 at the boundary. It's a non-trivial function. That function, however, is constrained. H inverse dH is a flat connection. And that implies that H should not depend on x minus. It is instead chiral. Finally, we actually have to impose the boundary condition that I advocated, namely that this quantity here in red is less singular than F inverse dF, which gave us the non-pole. So if you work that out, it's a constraint on the components, actually, of the matrix H. And what you find is that H is fixed by n minus 1 real scalars. And these are the Toda fields that we've been looking for. So what I've described for you can be understood somewhat more succinctly in terms of some older relationships between the WZW model and Toda. The non-boundary conditions are going to provide constraints on the WZW currents, which reduce it to Toda. And this is based on some old work here. Now, so far I've only discussed one boundary, a region near one pole, and it gave a chiral half of the Toda. But what about the full Toda? Well, it's known that if you have a manifold with two boundaries, and you look at Chern-Simons, then you end up with the full WZW model, as opposed to just the chiral WZW model. And our constraints are compatible with that. And so we're going to get two chiral halves, but they'll glue together nicely to make the full non-chiral Toda theory. Finally, let me just say some comments about the central charge. So Toda depends on a coupling constant B, which is a continuous parameter. And you can ask, what value of B did we land on? Well, the round force sphere in the explicit construction that I described gives the value B as 1. And so that tells you what the central charge of the Toda theory is. Now, of course, we'd be interested in recovering some B dependence, and we know how to do that, actually. So the way to do that is to deform the S4 geometry. You deform it. So the way to describe the deformation is think again of this equatorial 3-sphere. And instead of having the round 3-sphere, change it to what's called the squashed 3-sphere by changing the ratio of radii between S1 and S2. And then what you're going to do is fiber that over an interval, again having it collapse at the ends. And if you like, you can do a Weyl rescaling to stretch that out as well. And that will introduce some B dependence. So the ratio of radii here is some non-trivial function of B. Okay. Well, I think I've gone somewhat faster than when I practiced. So let me tell you some future directions. So obviously there's a lot still to do. I haven't mentioned anything about Toda vertex operators or 6D defects or punctures or anything like that. And it should be possible to really flesh all of that out. I mean, we have a very explicit construction of the Toda Lagrangian directly from 5 dimensions. That's one of the virtues of our construction. Is that although it can seem a little baroque to do 5D super Yang-Mills on a funny space, at the end of the day, it's just Kaluza-Klein reduction, and you get what you get. So it should be possible to flesh out AGT and maybe expand upon it. But a more long-term goal that I'd like to emphasize is that we can use similar techniques to study the 6D20 theory on other geometries. So one very promising case is the sixth sphere. You could try to do similar things, find some nice U1 and reduce there. And, well, that case is nice because it will lead to direct information about 6D correlation functions of local operators, not just D 6 minus D correspondences. So I hope to be able to tell you about that sometime in the future. Thanks for listening.